So now let's see how we can apply this theorem to series with non-constant sign. If you remember, if your series is positive, we can apply Beppe-Levy monotonous convergence theorem very naturally. So now what's happening if your series has term with a non-constant sign? So what do we have? We have a series S, well, the partial sums again are going to be Sn of x, and denote the sum from 0 to n of some un of x, which would have a non-constant sign. All right. Now we will need to have some pointwise convergence, just as before. So Sn of x converges almost everywhere to some value s of x pointwise, almost everywhere. And again, the idea is to find a dominating function. There exists g, a dominating function, so which is should be integrable. So what do we have? That for all x dominating function integrable. So for all n, we have that the partial sum Sn of x is smaller or equal to my g function. Okay, for all x, or almost everywhere. All right, so then we apply Lebesgue dominated convergence theorem. We have that the integral of the absolute value of the sum of the series, so the pointwise limit, is equal to the infinite sum of the un of x, the x of the integral of the un of x. All right? So this one is a pretty direct extension of this theorem for the series with maybe non-constant signs. So let's have one example. Let's put un of x is equal to -1 to the n times xn plus 1 times the log of x if x is between 0 and 1 and 0 and 0. Okay, and so of course that's a sequence which alternates the sign. We want to know whether we can compute first thing the sum of this series. So as from 0 to infinity, the sum of the un of x, does it converge to some nice function? So that's the first thing we have to find. And then if we can find a dominating function for the partial sums, then we can find that the sum of the integral is equal to the integral of the sum. Right, so sum of un of x, what is that? Well, we can factor with the log of x, and then we have the sum from 0 to infinity of -1 to the n x n plus 1. At that point, it should remind you of something that we. So you've got what is that sequence? You've got the sequence. Well, maybe we can the series. I mean, we can factor again with x. Sum of -1 to the n x to the n from 0 to infinity. So what is that? That's x times, so that's 1 minus x plus x2 minus x3 and so on. This is the sum of a geometric sequence of with minus x as the common ratio. So that's x times 1 over 1 minus x. Either you remember that from the geometric sequences, or you remember it from the power series that we did last year. So indeed, we have that the pointwise limit of this series is going to be, well, we've got x times ln of x times 1 over, 1 plus x, 1 minus the common ratio, so 1 over 1 plus x over 1 plus x. All right? Okay, so that's what denotes our s of x, the sum of the series. Next, if I want to find out that the integral of s of x is equal to the limit of, to the sum of the integrals of the un of x, let's find the dominating function. So to find the dominating function, when we have a series, what we can do is just very easily dominate every term and see the sum of this new series. So let's do this. Un of x equals to -1 to the n xn plus 1 ln of x. In terms of absolute value, well, the easiest thing we can get is get rid of the -1 to the n. So it's just going to be smaller than x to the n plus 1 ln of x. So that when I'm doing the sum, here, what do I get? I get x, ln of x, sum of the x to the n, and this one has a limit which is 1 minus x. Okay? X times ln of x times the sum of x to the n, and this is 1 over 1 minus x. Again, geometric series or whatever you can remember about power series that we saw last year. So that could be a nice dominating function. So that's dominating. We still have to see if it satisfies the integrability condition. So let's put g of x is equal to x times log of x divided by 1 minus x. Okay, is that integrable? All right, first of all, we still have to remember one thing, is that this convergence towards the s function, it has a convergence radius. Okay, anyway, we have a convergence radius, but it was also indicated that x is belong to 0, 1. So we just need to check out our integrability between 0 and 1. Okay, otherwise we should, well, maybe indicate that with an indicator function. All right, so what about the limit of this function? In 0, we have a continuous extension in 0. Or why? Because simply because g of x tends as x tends to 0. Well, the bottom just goes to 1 minus 0 is just 1, and the limit of x and ln of x as x tends to 0 is, well, 0. You should that's one of the few limits that you have to know by heart. And know how to prove that's even better. Okay, so that tends to 0 as g of x as x tends to 0. So we have a continuous extension in 0. What about the value in 1? You can substitute, well, in 1 as x tends to 1. So the problem now becomes at the denominator we have something that tends to 0, but at the top we also have something that tends to 0 because the log of 1 is 0. For this you can do simply a substitution. For instance, put capital X is 1 minus x, and now we're looking at the limit as x, capital X tends to 1 of so small x is equal to 1 minus big X times the log of 1 minus big X over capital X as x tends to 0. And so now the limit is small x tends to 1, capital X should tend to 0. So now at the top of this, that's going to go to 1, so there's no problem about that. And I have to find the limit of ln of 1 minus x over x as x tends to 0. Okay, and this you can do, for instance, power expansion of log of 1 minus x. Log of 1 minus x is just going to be minus x2 over 2 minus x3 over 3, and so on. So minus x power expansion minus capital X minus x2 over 2 minus x3 over 3, and so on. You divide it by x. The thing is that it tends to -1 as x tends to 0. So that tends to -1. So we also have continuity in a continuous extension in 1, so that the function is indeed integrable in 0 and 1, because I got rid, we proved that both problems could be just simply solved by looking at the limit, right? So what do we get? Conclusion from that part, we apply Lebesgue-dominated convergence theorem with the dominating function that we have found. Then we have that the integral between 0 and 1 of x ln of x over 1 plus x, which was, I remind you, the limit of the sum of my series, then that is equal to the sum of my series, which was indeed -1. Well, let's put that out of the sum sign, and then in the sum sign, what do I have again? X to the n plus 1 ln of x. Okay, I can also put the dx. Okay, that's half satisfying. What is going to be more satisfying is to compute this value and to get the real value of this infinite sum, so that we can find the value of this strange integral. Well, strange, not that much, of this integral, which is not that trivial to compute. So for this, I won't do it, but you can pause and go for the integration by parts. You will find that this value is -1 over n plus 2 squared. Okay, and so that finally you get that the value of this integral is going to be equal to the sum of -1 to the n plus 2 oh, sorry, plus 1 over n plus 2 squared. So -1 over the n at the power n plus 1 divided by n plus 2 squared. Okay. And if we give a bit more work, we can even compute the value of this sum. That's something that is doable with some basic tools, but which takes time. In the end, you would get that this sum is equal to pi squared over 12 minus 1. That's it. Okay, great.